So in this lecture, I will discuss about weak convergence of probability measures on R. So I will be working on R with the Borel sigma algebra, and I won't mention that anymore. And what I would like to consider is take a probability measure mu n defined on this space, and well, to define convergence of a sequence of probability measures to a probability measure mu. So maybe one of the first definitions you might consider is just, well, you'll say that mu n, or it's close to mu, if the supremum of mu n a minus mu a, it's small, where you take the supremum over all Borel sets A. And then you immediately realize that this is not a good definition. Let's take, for instance, two measures, mu and nu. So let's fix 2 points, x and y, and say that mu is the measure concentrated on a point x, and nu the measure concentrated on a point y. Just remind that the x represents the measure defined again on the Borel sigma algebra, such that, well, this expression is equal to 1 if x belongs to A, and 0 if x does not belong to A, where A is a Borel set. Then if you take that, if you consider the supremum over all A of the x A minus dy A, you realize that this supremum is equal to 1 whatever x and y. If as soon as x is different from y, if you take in this supremum A to be the singleton equal to x, this becomes 1, and you see that this is always bounded by 1, so this supremum is exactly equal to 1, no matter how far it's x from y. So this is not a good definition in view of this example. And, well, the problem is not in the supremum, because you could take the supremum, say, not in all sets A, but among all intervals. So if I call I the set of intervals, if you take again this supremum, you'll reach the same problem. So the proper definition is the following. I will say that in order to avoid this type of problem, we will say, and this is an important definition, that the sequence of probability measures mu n converge to a probability measure mu if and only if, well, for all intervals AB, mu n of the interval AB converge to mu of AB, but you restrict this definition to intervals AB such that the endpoints have zero mass with respect to A, so that the measure of the singleton A and the measure of the singleton B, it's equal to 0 with respect to the limit. So we will say that mu n converge in distribution, and this will be represented by that. So let me write, this is a convergence in distribution, or weak convergence, or weak convergence. We usually use weak for measures and distributions for random variables. I'll go back to that in 1 second. So I'll say that mu n converge weakly to a measure mu if for all intervals AB, such that mu of the singleton A is equal to mu of the singleton B is equal to 0, we have that mu n of the interval mind open at A and closed at B converge to mu of the interval AB. Well, it's clear that if I represent by Fn the distribution function associated to the probability measure μn, and by F the distribution function associated to the probability measure mu, this happens, and I leave it to you to check, if and only if Fn of x converge to f of x for all x which are continuity points of f, for all x which are continuity points of f. So we will say that the sequence of distribution functions Fn converge to a distribution function f if for all x which are continuity points of f, Fn of x converge to f of x. And remember, f it's a distribution function, so it's monotone. We assumed it, we fixed as a convention that f it's right continuous. So saying that fx it's a continuity point of f means to say that the left limit, which is represented by fx minus, so remember this is the limit as y increase to x of f of y, that this is equal to f of x. So for all such points, if Fn of x converge to f of x, we say that the sequence of distribution functions Fn converge in distribution to f. So we just define a new concept of convergence. We'll say that a sequence will converge weakly if, as we have seen, this happens. And this is equivalent to say that the sequence of distributions converge to all continuity point of x. And we will extend now this definition to random variables. So now if I have a sequence xn of random variables, I will say that xn converge in distribution or in law to x if the distribution function of the random variable xn converge weakly or converge in distribution to the distribution function of the random variable x. So this is a definition, and mind the following, that convergence in probability and almost sure convergence or LP convergence required that all random variables were defined on the same space. Here, in this definition, we are not requiring xn and x to be defined on the same space. Maybe xn, each random variable is defined on some probability space omega n, fn, and pn. X also is defined on some other space. We still can make a sense to this distribution since it involves only the distribution functions or the induced measures on R. So now in this definition, there is a big advantage, is that these random variables need not to be defined on the same probability space. So let me recall what the distribution function is. So this a function f defined from R to 0, 1. It's called a distribution function if it has three properties, and we have seen that before. The first one, we require f to be monotone, increasing. So this means that if x it's smaller than y, then f of x it's less or equal than f of y. Then we required f to be right continuous. And here, mind that this is a choice. We could have chosen f to be left continuous, as some others, but here I'm assuming that f it's right continuous. And since f it's monotone, of course it has left limits. And finally, The third property is that as f approaches to plus infinity, f of x approaches 1, and if x converges to minus infinity, f of x converges to 0. So this means that limit of x, as x goes to infinity of f of x, it's equal to 1, and the limit as x goes to minus infinity of f of x, it's equal to 0. So this is the set, the class of distribution functions. And I will represent this class by the letter n. So throughout this lecture, n will represent the set of distribution functions, so the set of functions which satisfy this condition. Now, I will define a larger set just to be able to state in a simple way my first theorem, M. So M is a larger set, and M will, the set of elements of f are all those functions g from R to 0, 1, such that, well, they satisfy 1 and 2, which means that the functions g in M are monotone and are right continuous with left limits, but instead of asking the limits to be equal to 1, I will relax this assumption and ask that the limits as x goes to infinity it's less or equal than 1, and the limit of f of x as x goes to minus infinity it's larger or equal than 0. So 3 is replaced by 3 prime, which states that the limit as x goes to plus infinity of g of x, it's less or equal than 1, and the limit as x goes to minus infinity of g of x, it's larger or equal than 0. So 1, 2, and 3 prime defines the set M, which contains, of course, the set N. And I can extend the definition of convergence. So I'll say that if you have a sequence Gn in M and G in M, I'll say that the sequence Gn converge in distribution to G. So I'm extending the definition of convergence in distribution, which is originally defined in N, to M, just by saying, well, that this sequence converges to that one if and only if for all x such that g of x it's equal to gx minus, so for all continuity points of the function g, we have that the limit of n of gn as n goes to infinity of gn of x, it's equal to gx. So this extends the concept of convergence in distribution to the set M. And now I can define my main first theorem. So let me erase the definition of M. So the theorem, which I want to prove now, states the following. Well, consider sequence Fn in the set N. I could replace here n by m, but since in this lecture I will always use this result for distribution functions, I'm stating it in this way. So consider sequence Fn of distribution functions. Then what I claim is that there exists a function g in M. So let me call that in large distribution, say, G, and there exists a subsequence nk such that the subsequence fnk converge in distribution to G. So this theorem is telling me that if you consider any sequence of distribution functions, you can always find a subsequence and an element of M, so an enlarged or generalized distribution function. So let me call them generalized distribution function, such that f and k converge in distribution to G, where by convergence in distribution we are talking about this concept. So this is the theorem which I want to prove now. So I restated here the theorem. We have a sequence Fn of distribution functions, and I want to prove that there exists a distribution in M and a subsequence nk, such that f and kx converge to g of x for all continuity points x of g. So the proof is performed in 3 steps. So I'll present now the first step. The first step will be to construct the subsequence nk. So for that, let me represent by R1, R2, R3, and so on. This is an enumeration of the rational numbers. Let me consider now the sequence Fn of R1. So I'll fix the first element of my enumeration of the rational numbers, and now I consider the sequence in n of Fn R1. So this is, since Fn is a distribution function, this is an element of 0, 1. Now, since this sequence it's a bounded sequence, I know that I can obtain a subsequence which I will represent by n1. So this is a subsequence of the original sequence, or maybe n1 of k, a subsequence of the original subsequence such that fn1 of k of x converge to some limit, and here it's not x but r1, such that this sequence converge to some g r1. So since this sequence is bounded, I can find a subsequence which converge, and I'm representing this subsequence by n1k. Now I take this subsequence and the second element of my enumeration, and I have now n1k of R2. This again, it's a sequence in n1k of numbers, real numbers in the interval 0, 1. And therefore, since this sequence is bounded, I can find a subsequence of this sequence. So I'm representing by n2k a subsequence of the sequence n1k, such that fn2k R2 converge to some real number which belongs to the interval 0, 1, which I'm representing by gr2. Now I can repeat this procedure for all elements of Q, and by using Cantor diagonal procedure, I can obtain a subsequence which I will represent by nk, so a subsequence of the original sequence, such that for all j, f nk rj converge to g rj. So I obtained in this way a subsequence nk which has the following property: for all rj, for all rational numbers, f and k of rj converge to g rj. It's clear that g rj belongs to the interval 0, 1 because the sequences belong to the interval 1, and it's also clear that this sequence is monotone. So if I take rj smaller than rl, so two rational numbers, one which is smaller than the other one, then I claim that g rj it's less or equal than g rl. And this is clear because g rj is the limit of f and k rj. F and k is a distribution function, which means that since rj is smaller than rl, f and k rj is less or equal than f and k rl. And since we have two sequences, one bounded by the other one, the limits are bounded, and from that we conclude that we have this inequality. So this is the end of step 1. So up to this point, we constructed a subsequence nk with this property and the limits g or j belong to 0, 1 and defined on all rational numbers of R, and they are monotone on the rational numbers. So I just wrote what we proved up to now. We proved the existence as a subsequence such that for all rational number R, g and f and k of R converge to g of R, and g, this function which is defined on the rational numbers, has the following property: g of R belongs to 0, 1, and it's monotone. If R and S are two rational numbers, R less or equal than S implies that gr is less or equal than gs. Now comes step 2. I'll define a function. Here's the definition of this function. G of x will be equal to the infimum of g of R for all R larger than x. So here R, it's a rational number. Right, so I'm taking the infimum of g of R over all R which are rational numbers, because g is defined only over rational numbers, and over all rational numbers which are larger than x. And this is the definition of G. What I claim is that G belongs to the set M, which means that G is a generalized distribution function. So let's prove. So to show that G belongs to M, we have to prove 3 properties. First, that G is monotone. So let's take x smaller than y, and I want to prove that g of x it's less or equal than g of y. So x it's smaller than y, and now I look at these sets. The infimum, the set of all r's, rational numbers, such that R it's larger than x, and the set of numbers R such that R it's larger than y. Well, if R it's larger than y, then it's larger than x, so this set it's clearly contained in this set. So if R it's a rational number which is larger than y, it's also larger than x, and therefore it's an element of this set. So this means that if I'm taking an infimum, so let me call maybe this set the set AX, and this is the set AY. So just prove that AY is contained in AX. This implies that if I take the infimum of a function gr for R in a set AY, and I compare that with the infimum of gr for R in AX, well, since this set AY it's contained, I'm taking an infimum in a smaller set. And the infimum in a smaller set has to be larger than the infimum in a larger set. So since AX contains AY, if I take the infimum in this larger set, the infimum will be smaller than the infimum in this smaller set. And this is exactly the definition of Gx, while this one is the definition of Gy. So we proved that indeed G of x it's less or equal than G of y, therefore G is monotone. So this is the first property of the function G. Now the second property is that G is right continuous. So we want to show that G is right continuous. So let me take a point X and let me fix maybe an epsilon positive. So I want to prove that there exists a delta such that if I take any point between x and x plus delta, gy it's less or equal than g of x plus epsilon. So I want to prove the existence of this delta such that for all y belonging to the interval x plus delta, g of y it's less or equal than gx plus epsilon. Fine, so this epsilon is fixed. And now let's recall the definition of g of x. So g of x, it's equal to this infimum. So I'm taking here g of r, and I'm taking all the rational numbers, and I'm taking the infimum of these g of r. So what I claim is that, well, since this is the infimum, and this limit, this infimum, it's a finite real number, because g of x belongs to 0, 1. That I didn't prove, but I will prove it in a second. So since g of x it's a real number, well, you can get as close as you wish to this infimum, and therefore there exists an r in this space. So an r which is a rational number and which is larger than x, which almost attains the infimum. So such that g of r it's less or equal than gx plus epsilon. Right? So g of x it's the infimum. Since it's a real number, this infimum it's almost attained. What does it mean that it's almost attained? That means that if I fix an epsilon, I can find one which is almost equal to the infimum, which is therefore, what does it mean to say it's almost equal to the infimum, gx? It means that, well, there is one which is bounded by gx plus epsilon. So let me write that in the following way. Well, g of x, it's larger than g of r minus epsilon. And now, well, r it's larger than x. So I obtained here, let me call this r, maybe r0 to distinguish it from the other ones. There is some, so is x. I found here r0, which is a rational number larger than x, which has this property. Now here is my delta. So delta will be equal to r0 minus x, and this is strictly positive because r0 it's larger than x. And what I claim is that any point here, so let me take a point here, satisfies this inequality. So let's take y, which belongs to the interval x r0. And let me take it open at r0. So g of y, by definition, it's the infimum over all s in Q of all g of s such that, well, s it's an element of Q and s it's larger than y. So now mind that here I'm taking some point y, and I'm taking now the infimum of gs for all s rational number larger than y. But R0 is a rational number which is larger than y, because y belongs to this interval. Since y, R0 is a rational number which is larger than y, it belongs to this set, and therefore it's larger than this infimum. So this is smaller than g of R0. Right? Since R0 is a rational number which is larger than y, this infimum is smaller or equal than g of R0. And g of R0, it's less or equal than gx plus epsilon. So I just proved that if you take any point in this interval x and opened at R0, g of y, it's bounded by gx plus epsilon. So since I want to remove this point delta, let me take delta, not this difference, but this difference divided by 2. So delta will be something like that. And I indeed proved that for any point in this interval between x and the medium point between x and R0, for any point in this closed interval, indeed I have that g of y is less or equal than gx plus delta. Or if you accept to have an open interval, I can take delta, as I said before, equal to R0 minus x. So this proves that indeed g is right continuous. Right? So maybe I'll repeat that to make sure that you understood. To show that it's right continuous, what I need to show is that for any fixed epsilon positive, I can find a delta such that, strictly positive delta, such that for any y in this interval, g of y, it's bounded by gx plus epsilon. And of course I can take it open here or closed here, so it's simpler if I take it open. So let's prove that. To prove that, let's recall the definition of g of x. G of x is given by this infimum. I'll show in a second that g of x belongs to the interval 0, 1, so it's a real number. And therefore this means that the infimum is almost attained, which means that I can find for that fixed epsilon a rational point, so an element in this set, so a rational point which is larger than x, such that, well, g of R0 it's almost equal to the infimum, which means that g of R0 it's less or equal than g of x plus epsilon. Fine. So now let's draw the picture. Here is x, and I found here is R0, which is a rational number, larger than x. So now I want to take delta to be the size of this interval, which means that delta is equal to R0 minus x. And this is strictly positive because indeed R0 is larger than x. And now I claim that any point in this interval, so closed at x and open at R0, any point y in this interval satisfies this inequality. And why is that true? Well, take a point y in this interval. By definition, g of y is the infimum of g of s for all rational numbers s which are larger than y. Well, R0 is a rational number larger than y, and therefore R0 belongs to this set, and which means that the infimum is less or equal than g of R0. Now remember that g of R0 is bounded by g of x plus epsilon, and this tells you that g of y it's indeed less or equal than g of x plus epsilon. So what did we show? We showed that if we take delta this size, indeed g of y it's bounded by g of x plus epsilon, which proves that G is right continuous at X. So now we proved, up to now we proved that the function G defined by this formula, it's monotone, it's right continuous provided that G belongs to the interval 0, 1. So now let's prove that now G of X belongs to the interval 0, 1 for all X in R. And well, this is clear because we know already that G of R belongs to 0, 1. So it follows from this formula that G of X it's larger than 0 because, well, each of G of R it's larger than 0, then thus the infimum it's larger or equal than 0. And also that G of X it's less or equal than 1 because, well, you take any R larger than X, rational number, G of R it's bounded by 1 and therefore the infimum it's bounded by 1. So these two properties are elementary and therefore G of X indeed belongs to 0, 1 for all X. In particular, this completes the proof of claim B, which was saying that G is right continuous, because at some point we use this fact without proving it. Now, since G is monotone, the limit as X goes to infinity exists. It exists because G is monotone. It's bounded by 1 because Gx it's bounded by 1. And the limit as X goes to minus infinity of G of X exists because, again, G it's monotone and it's larger or equal than 0 because G it's larger or equal than 0. Which means that we proved the three properties of generalized distribution function. So up to in the second step, we define G by this formula, and indeed we proved that G it's a generalized distribution function. So in step 1, we proved the existence of a subsequence nk for which f and k of R converge to G of R for all rational numbers R. And in the second step, we introduced this function G, and we proved that G it's a generalized distribution function. So now step 3, we want to show that f and k of X converge to G of X for all X which are continuity points of G. So fix X a continuity point, so G of X it's equal to Gx minus. And I want to show that Fn of X converge to G of X. So here is X, and since I fix an epsilon positive, and since G of X it's continuous at X, this means that there exists a point, a delta, such that all points, so that Gx minus delta it's larger than G of X minus epsilon. Right, G it's monotone, so I don't need just to claiming that G of X minus delta it's larger than that means that all points in this interval on the left of X are larger than Gx minus epsilon, and Gx plus delta it's less or equal than Gx plus epsilon. Right, since G is monotone, saying that G is continuous at X means that for any epsilon you can find such a delta. Fine, so now let's take two rational number, let's say R and S, and say that S belongs to the interval x plus delta, and R to the interval x minus delta x. R and s are rational numbers. And I will prove an upper bound and a lower bound for f and x. So f and x, f and kx, well, f and k it's a distribution function, so it's bounded by the value of f and k at s. Right, because, well, it's a distribution function, so it's monotone. Now, by assumption, since s is a rational number, f and k of s converge to g of s. Now, g x plus delta, it's equal to the infimum of g of t, where t it's a rational number and t is larger than x plus delta. Well, since t it's larger than x plus delta, t it's also larger than s. And since g it's increasing, this means that all elements gt here it's larger than g of s. So this means that g of s it's smaller or equal than g of t for all elements t in this set, which means that g of s it's also less or equal than the infimum, and the infimum is g x plus delta. So this means we just proved that g s it's less or equal than g x plus delta. And by construction of our delta, gx plus delta it's bounded by gx plus epsilon. So this proves that the limit sup of f and kx it's bounded by gx plus epsilon. So we just proved, let me write it here, we just proved that the limit sup in k of f and kx it's less or equal than gx plus epsilon. So let me repeat the argument to make sure that it's clear. I have this sequence f and kx, which I want to bound. Well, first I use the fact that f and k it's a distribution function to say that f and k at x it's less or equal than f and k at s, because s is larger than x. Now let me recall the definition of g. We know that this sequence f and k converge at the rational numbers to g. So the limit of this sequence is equal to g of s. Now let's recall what's the definition of g at x plus delta. G at x plus delta is the infimum of gt for all rational t's which are larger than x plus delta. Now what I said is that, well, if you compare s with t, since t is larger than x plus delta, since g is monotone, g of s it's larger than g, it's smaller or equal than g of t. And this happens for all t in this set, and therefore the infimum it's also larger or equal than g of s. So this means that g of s it's less or equal than gx plus delta, and by definition of delta, gx plus delta it's bounded by gx plus epsilon. So this sequence it's bounded by that one, and that one converges to a number which is smaller than this one. Therefore, the limit sup of this sequence it's bounded by the same expression. So this says that the limit sup of f and kx it's bounded by gx plus epsilon. So we proved that the limit sup of f and kx it's bounded by gx plus epsilon. Now let's prove the other bound. So again, we start with f and k of x. But now kx it's larger than r. So this is larger than f and k of R, and f and k of R converge to G of R. Now, R, it's larger than x minus delta, so let's recall Gx, the definition of Gx minus delta. Gx minus delta is the infimum of Gt for all t which are rational numbers and for all t larger than x minus delta. So I'm taking an infimum here over all these sets. Well, it turns out that R belongs to this set. R is a rational number and it's larger than x minus delta. So this means that this infimum, it's smaller than G of R, because G of R is just one element. So this tells me that this infimum, it's smaller than G of R. So in other words, G of R, it's larger than Gx minus delta, and by our choice of x of delta, Gx minus delta, it's larger or equal than Gx minus epsilon. So let me repeat the argument again to make sure that everything is clear. I want to get a lower bound for the limit of f and k x. I first realize that x is larger than R, and therefore, since f is monotone, that f and k at x it's larger than f and k at R. Now f and k at R, I know it converges to G of R. So as k goes to infinity, this sequence converges to G of R. Now here I recall the definition of Gx minus delta. Gx minus delta is the infimum of Gt for all t which are rational numbers larger than x minus delta. And mind that R is a rational number and that R is larger than x minus delta. Therefore, R belongs to this set, and therefore the infimum of Gt over this set is smaller or equal than G of R. So this is what we wrote here. G of R is larger or equal than Gx minus delta. And now by definition of this delta, Gx minus delta, it's larger or equal than Gx minus epsilon. And therefore, since this sequence converges to a limit which is larger than that one, the imp of this sequence it's larger than Gx minus epsilon. So now we proved that the limit sup of f and kx is less or equal than Gx plus epsilon. Limit imp it's larger or equal than Gx minus epsilon. Since this is true for all epsilon positive, we conclude that the sequence f and kx converge, and it converges to G of x, and this is exactly what we wanted to prove. So this completes the proof of this theorem. We proved that indeed there exists an element G of M, which means indeed it exists a generalized distribution function and a subsequence f and k, such that f and kx converge to G of x for all continuity point x of G, which means that f and k converge in distribution to G. So just let me insist on that. So a remark. In this theorem, G belongs to M. So G is a generalized distribution function. So let me just give you an example to show that indeed G may not belong to N. So let's take mu n, the Dirac mass on the point N. So remember this is mu n puts a mass equal to 1 on the set on the point N. And this means that the distribution function Fn looks as follows. Well, it's 0 up to n. At n it jumps to 1, and it's 1, so it's right continuous, so it's 1 at n, and 0 at the left of n. And so you see that, of course, this sequence f and x converge to 0 for all x in R. And this 0 is an element of our set M. So here's an example of a sequence of distribution functions which is converging in distribution to a generalized distribution function which is identically equal to 0. And of course you can replace n by minus n, in which case that will be the distribution function will be 0 up to minus n and 1 starting from minus n. In that case you will converge to 1 for all x. And again, you have here an example of a distribution function, sequence of distribution functions, which is converging to degeneralized distribution functions, which is constantly equal to 1. So these are examples saying that we cannot improve our theorem replacing the set M of generalized distribution functions by the set N of distribution functions. So what we proved is that, well, if you have any sequence, you can find a subsequence which converge. Now, what I will prove next is that if you have uniqueness of limit points, then the sequence converge. The whole sequence converge. So this is the next result. So let me repeat. We proved that from any sequence we can extract a subsequence which converge. Now what I claim is that uniqueness of limit points implies convergence. So let me state what I mean by that. So this is a lemma. So I'm considering again a sequence Fn of generalized, say, distribution functions. And I'm assuming that there exists uniqueness of limit points. So what does that mean? I'm assuming that there exists a G0 in M with the following property, that if I have a subsequence f and k which converge in distribution to some G, then G is equal to G0. So this is what I mean by uniqueness of limit points. There exists one generalized distribution function with the following property: any subsequence f and k which converge in distribution, so let's say that f and k converge in distribution to some G, then G has to be equal to that one. If we can prove these uniqueness of limit points, I claim that we get that the sequence and not only subsequence converge to this unique limit point. So this is what I want to prove now. So I restate here the theorem, and here's the proof. The proof goes by contradiction. So assume that Fn does not converge in distribution to G0. What does it mean that a sequence does not converge in distribution? This means that there exists a continuity point x. So this is a continuity point of G0 such that Fnx does not converge to G of x, G0 of x. Well, Fn of x, it's a sequence in the interval 0, 1. Saying that it doesn't converge to G0 of x is to say that you can find a subsequence which is far from G0 of x, but from this subsequence I can extract a converging subsequence. So we get from this that there exists a subsequence nk such that f nk of x converge to some number a, which is different from G0 of x. Right, saying that this sequence of real numbers bounded by 0 and 1 does not converge to G0 of x is saying that there exists a subsequence which stays far from G0 of x, but from this subsequence I can extract another subsequence. I can extract a further subsequence which converge to a point, and since it stays away from G0 of x, this point, it's different from G0 of x. So I hope that you understood that if this is the case, then I can extract a subsequence f and k such that f and k of x converge to some number a, which is different from G0 of x. Now I can apply the theorem. The theorem gives me a further subsequence, so let me call that n1k. So this is a subsequence of that subsequence, and I can find a g such that f n1k converge to g in distribution. So the theorem tells me that, well, consider this sequence f and k of distribution functions. I can find an element g of m and a subsequence, which I'm representing by n1k, a subsequence of this subsequence, such that f n1k converge in distribution to g. Now, by assumption, I have here a subsequence which is converging in distribution to g. So by assumption, g has to be equal to g0. So I have that actually f n1k converge in distribution to g0. This is what the hypothesis of this lemma tells me. Well, but x, it's a continuity point of g0. So I get from that, since I have convergence in distribution, is that f n1k of x converge to g0 of x. And here I get a contradiction because f and k of x is converging to a different from 0, and this subsequence is a subsequence of that sequence. So I get here a contradiction which proves my claim. So this result gives me a strategy to prove that a sequence of distribution functions, so say that you started with a distribution function and you want to prove that fn converge to some g in M. Well, this lemma is telling me that the only thing I need to prove in order to show that this sequence converges to G is to prove uniqueness of limit points. So if I prove the following statement for this sequence Fn, I proved that Fn converges to G. So what I need to show is that there is uniqueness of limit points, which means that if I take a subsequence of this sequence, and if I assume that this subsequence converges to some, let me call that G0, so I want to prove that Fn converges to G0, what I have to prove is that G0 is the unique limit point. And how do you prove that? Well, assume that there exists a subsequence f and k which converge to G, then you have to show that G is equal to G0. So if I'm able to prove this statement, which means uniqueness of limit points, then this lemma is telling me that Fn actually converge to G0 of M. What's annoying in this strategy is that I started from distribution functions and I end up with a generalized distribution. So now in the rest of this lecture, I will introduce sufficient and necessary conditions to guarantee that this G0 actually belongs to N, which means that this generalized distribution function is actually a distribution function. So my next topic now is to find conditions which guarantee that this limit is actually a distribution function. So here is a definition. Let's say that I have a family mu alpha, alpha in some index set I, which does not need to be countable. Suppose that you have a family mu alpha, and that these mu alpha are probability measures on R. I will say that this family is tight if the following condition holds. For any epsilon positive, I can find a epsilon, an interval a epsilon, b epsilon, such that mu of alpha of a epsilon, b epsilon, the measure of this interval is uniformly in alpha larger than 1 minus epsilon. So this family is tight if for any epsilon I can find this finite interval. You can replace this finite interval by a compact set k epsilon. Leave it to you to check that this is equivalent. Compact set k epsilon, such that the measure of this compact set, or the measure of the interval a epsilon b epsilon, it's larger than 1 minus epsilon, and this uniformly in alpha. So for all alpha in I. So this is what's called a tight family. Of course, this condition can be replaced by distribution functions, saying that f, you can find a epsilon and b epsilon such that f alpha of b epsilon minus f alpha of a epsilon, it's larger than 1 minus epsilon for all alpha in I. So the family of distribution functions will be said tight if for any epsilon you can find b epsilon and a epsilon such that f alpha of b epsilon minus f alpha of a epsilon, it's larger or equal than 1 minus epsilon for all alpha in I. And the theorem, which I want to prove now, is the following. Let's say that you have a sequence fn of distribution function. Then what, so these are elements of n. And what I claim is that fn is a tight family if and only if the following holds. If f and k converge, so if I have a subsequence f and k which converge to G, so the statement is the following: for all subsequence nk such that f and k converge to G, then G is a distribution function. So let me read again the statement of this theorem. So assume that you are given a sequence of distribution functions. What I claim is that this sequence is tight, according to this definition here, if and only if the following property holds. Well, for all subsequence nk such that f and k converge to an element G of M, then G actually belongs to N. So what we are going to use here is that we are going to use this theorem usually in the following way. Well, you have a sequence Fn. You know that it converges. you want to show that the limit belongs to n. So what you need to prove is that it's tight. Because by proving that it's tight, since you know that it converges, this theorem tells you that it converges to a distribution function. So this is, so we are going to use this result in this direction, but is actually this condition of tightness is sufficient, as we have seen, but it's also necessary for G to belong to N. So just to say that we are not introducing here a too strong condition in order to guarantee that the limits are distribution functions, we will prove also that this condition is necessary. So I stated again this theorem. So mind that I replaced a countable sequence by an uncountable one. We will prove this slightly stronger version of this theorem. And before I proceed, suppose that you can take a family of one element. So let's say that f it's an element of M, and you say that f it's tight. Then what I claim is that f it's actually a distribution function. And this is clear because, well, to show that f it's a distribution function, you have to show that the limit as x go to infinity of f of x it's equal to 1, right? And the same result by in the limit of x going to minus infinity, but I'll concentrate it on that one. The proof of the other one is similar. So I have to show this, but I know that f it's tight. So I know that if I fix a positive epsilon, I can find a epsilon and b epsilon such that f of b epsilon minus f of a epsilon, that this is larger than 1 minus epsilon. But of course, f a epsilon it's positive, so f of b epsilon it's larger than f b epsilon minus f a epsilon. And therefore f, we know that there exists a b epsilon such that f of b epsilon it's larger than 1 minus epsilon. And since f it's monotone, this means that f of x for all x larger than b epsilon are larger than f b epsilon, which is larger than 1 minus epsilon. And therefore, since f is monotone, this limit exists. And what this is telling you is that this limit is larger than 1 minus epsilon for all epsilon, which means that the limit is equal to 1. So if I know that a distribution function, a generalized distribution function is tight, I get that it's actually a distribution function. And what this theorem is saying is that, well, this holds for a family, which means that, well, if you have a family which is tight, the limit also will be a distribution. So let's prove one side of this claim. So what I just said, maybe in not a very clear way, is that the proof that this property entails that one, it's essentially a generalization of the argument I just gave. So let's assume that this family is tight. And let's consider a sequence f alpha k, which is converging in distribution to some g in M. And what I want to show is that g is actually a distribution function. So I want to use exactly the argument I gave to prove this claim. So to show that g is a distribution function, I have to show that the limit as x goes to infinity of g of x it's equal to 1, and that the limit as x goes to -infinity of g of x, it's equal to 0. Now let's use the fact that f alpha is tight. Let's fix some epsilon positive. The tightness tells me that there exist alpha epsilon and b epsilon such that f alpha of b epsilon minus f alpha of a epsilon, that this is larger than 1 minus epsilon for all alpha in I. So here is a epsilon and here b epsilon, and what I know is that this difference is larger than 1 minus epsilon. Now I know that f alpha k convergent distribution, g, it's a monotone function. So it's a monotone function. So remember that a monotone function, for a monotone function, almost all the number of discontinuities is at most countable, which means that the number of continuity points is dense in, well, it's a set minus a set which is at most countable. So we can find to the right of b epsilon a point, let me call it y, which is a continuity point of g. So I'm taking y larger than b epsilon, which is a continuity point of g. Such a point exists because, as I said, the discontinuity points of g are at most countable. Now, since f alpha k converge to g, we have that f alpha k of y converge to g of y. So g of y, it's equal to the limit in k of f alpha k of y, but y it's larger than b epsilon and f alpha k it's monotone, so f alpha yk it's larger than f alpha k b epsilon, and therefore since f alpha k b epsilon it's larger than f alpha k y, this limit it's larger than the limit inf or the limit sup in k of f alpha k b epsilon. And now I go back to my bound here. I repeat the bound I used before. So f alpha k of b epsilon, it's larger than f alpha k b epsilon minus f alpha k a epsilon, because this is positive, and this is larger than 1 minus epsilon, so this limit sup, it's larger than 1 minus epsilon. So I proved that for any continuity point y at the right of b epsilon, g of y is larger than 1 minus epsilon. And this proves, therefore, that the limit as x goes to infinity of g of x is larger or equal than 1 minus epsilon. So I leave it to you to check that the other limit is equal to 0, which proves that indeed, if this sequence is tight, any subsequence which converge in distribution to an element, a generalized distribution, the generalized distribution is actually a distribution. So this proves one direction of the theorem. Now we want to prove the converse statement. And the converse statement will be proved by contradiction. So to prove it by contradiction, I have to remind you what tightness means. So tightness means that for all epsilon positive, I can find an interval, so points a, b, a less than b, such that for all alpha in I, f alpha b minus f alpha a, it's larger than 1 minus epsilon. So by contradiction, I'll assume that this family is not tight, and I will prove that in this case this statement does not hold. So let's assume by contradiction that this family is not tight. So we have to say that this statement is not true. This means that there exists an epsilon such that for all A less than B, there exists an alpha in I such that f alpha B minus f alpha A is smaller than 1 minus epsilon. That's fine. So let's assume it's not tight. There exists an epsilon such that for all AB, so let me take, since this is true for all AB, let me take A equal to minus n and B equal to n. So for this choice, minus n, n, I know that there exists an alpha, which I will call it alpha n, such that f alpha n B minus f alpha n A, f alpha n n, sorry, f alpha n minus n, that this is less than minus epsilon, 1 minus epsilon. So this is what's telling me, so I will just erase and keep the fact that I know there exists an epsilon and a sequence alpha n such that this holds. So there exists a sequence alpha n such that f alpha n of n minus f alpha n of minus n, that this is less or equal than 1 minus epsilon. So this is what I know, and now I will prove that this statement is not true. So I'll find a sequence alpha k, well, this is the sequence, such that f alpha n converges to G for a G which is a generalized distribution. It's not, I'll show that G is not a distribution. So how do I proceed? I'll use the first theorem of this lecture to obtain from alpha n a subsequence alpha n1 such that energy in M such that f alpha n1, so a subsequence of this one, converge in distribution to G. So I'm starting from this sequence and I'm applying the first theorem to extract from this sequence a subsequence and to find a generalized distribution G such that f alpha n1 converge in distribution to G. Now I want to prove that G does not belong to n, to show that if this is not true, then this statement is also not true. Fine. So let's fix 2 points x and y. For that fixed point x and y, let me take y0 and x0. So x0 is smaller than x, y0 is larger than y. y0 it's a continuity point of G as well as x0. So I know that G of y minus G of x, it's smaller. So G of y is smaller than G of y0 because G is monotone. And G of x it's larger than Gx of 0 because G is monotone. So Gy minus Gx it's bounded by Gy0 minus Gx0 because G it's monotone. Now y0 and x0 are continuity points, so they are the limit. Since we have convergence in distribution, this is equal to the limit in n of f alpha n1 y0 minus f alpha n 1 x0. Now, for n sufficiently large, so for all n such that n is larger than y0 and minus n it's larger than x0, again, fy0 it's bounded by fn, fx0 it's larger than f minus n, so this is smaller than f alpha n1 of n, because we have this condition. So this n is the n which corresponds to that subsequence. I hope you understand it. Right, so here we extracted subsequence, so this n is the n which corresponds to this extracted subsequence, and now we apply this inequality, so this is larger, so fy0, because y0 is smaller than n, it's bounded by that one, this is larger than this one, so we get that this difference, it's bounded by the limit sup of, or the limit inf of this sequence, right? This term it's bounded by that one. This one it's larger, but we have a minus sign. So this difference it's bounded by this difference, and therefore this limit it's less or equal than the limit inf of this sequence. And by this condition, this expression, it's bounded by 1 minus epsilon. So we took any y and x such that y is larger than x, and we proved that the difference g of y minus g of x, it's bounded by 1 minus epsilon. Since, well, this is true for all y and x, we can send x to infinity to prove that g of y, it's, well, this cannot be a distribution, because if I send y to infinity and x to minus infinity, this difference will be always bounded by 1 minus epsilon, and therefore this quantity cannot converge to 1, or if this quantity converges to 1, this one cannot converge to 0. So one of the two limits will fail, because if the first limit, if the limit of g of y when y tends to plus infinity, it's 1, this proves that this limit cannot be equal to 0, because otherwise this bound will be wrong. So the fact that g of y minus g of x is bounded by 1 minus epsilon for all y x shows that g cannot be a distribution function, and therefore proves that this statement is wrong. Therefore, if the thesis is false, then the conclusion is false, and that proves the second part of this theorem. So the conclusion of this lecture is the following. Let's say that you have a family Fn of distribution functions, and you want to prove that Fn converge. Then, in view of this lecture, what you have to prove first is uniqueness of limit points. Uniqueness of limit points, as I said, is the following. Suppose that Fn, so there exists G0 with the following property. Assume that Fnk converge to G, then G is equal to G0, and this is an element of M. So this is one result we proved. In order to show that Fn converge, it's enough to show that there exists a unique limit point. The problem is that this limit point may belong to M, and to show that this convergence takes place, convergence, you converge to an element of n, you converge to a distribution function, you have to prove that this sequence Fn is tight. So this is the general method which will be used in order to prove that a sequence of distribution function converge to a distribution function. You first show that this sequence is tight, and then you prove uniqueness of limit points. With these two results, by the theorems we just proved, you deduce that indeed your sequence Fn converge to some distribution function.